And where that's going to move into is our 4+ member transition states. I believe I've called them just 4 in the past. In this subclass of our electrophilic additions, we have an insanely small leaving group. So that when the pi bond comes out and attacks the Lewis acid, okay, the leaving group that's connected to that Lewis acid is so small that it can't exist on its own. Which means instead of the Lewis acting as a nucleophile to share electrons back down, the leaving group is what shares electrons back down. And what we end up forming is a new kind of 4-membered transition state. In the 3-membered, we could actually form intermediates. In the 4-membered, we don't really form those intermediates per se. The larger ones, like 5-membered transition states, we actually form those intermediates. Okay? So if we take a look at the examples shown down below, the classic example is looking at our borane, or BH3, or, because everybody likes being irritating with names, sometimes you'll also see B2H6. So all getting at the same kind of general concept. Why B2H6 and not BH3? Because officially the structure is unstable as BH3 and it dimerizes on its own to form B2H6. So on a test, you're more than likely going to see B2H6 because that's how it forms. That's how it would go into the solution. As soon as it hits solution, it acts like BH3. And that's what's being shown right underneath. Our boron, having only 3 groups of electrons, is sp2 hybridized. It has an empty p orbital. That empty p orbital can accept the pi electrons from our nonpolar pi bond, okay, like our alkenes or our alkynes. Boron has now exceeded its happiness with the electrons, and it will immediately kick out its leaving group. That leaving group would then be hydride, H-. Is that stable? No. It is too small and too low in electronegativity to actually stabilize that negative charge. So instead of going out into solution and free floating around, those electrons immediately swing in to attack the other end of our pi bond. Because our pi bond, the electrons are being shared between 2 carbons. If the electrons come out to share with the boron, one of those carbons is now lacking electrons. That carbon is where the hydride is going to come in and attack. And what we end up showing is kind of what that image is trying to show with the dashed lines. As a transition state, how many atoms are in that? 4. I get the hydrogen, I get the boron, and I get 2 carbons. There's my 4-membered transition state or intermediate. Okay? Notice the end result is that we don't end up seeing the 4-membered ring. Okay? We go from a pi bond to the fully added structure, okay, with the boron attached. Kind of makes sense? Why are we concerned about that 4-membered transition state? Well, if we look at the product, we've added 2 new sigma bonds, the hydrogen and the boron. Where did those new sigma bonds add?
On the same side.
The same side of the pi bond, which means we get a syn addition. That forces very particular stereochemistry in our products. So we have to be careful when we go through and evaluate that to make sure that that stereochemistry shows up. Okay? The other part that this one kind of brings in that I find, of course, frustrating is notice we've added a hydrogen. Okay? We've done that before. In fact, when we looked at hydrogen being added to a double bond, we classified it according to Markovnikov. The hydrogen went to the position that was more less substituted. Okay? And that was Markovnikov's rule. That's where the hydrogen goes. Well, that's because the hydrogen that we typically see is what charge? Positive. What is the charge on a hydrogen in this case?
Negative.
Negative. The hydrogen ends up going to the less likely position, okay, or in an anti-Markovnikov fashion because its charge is different. And this again goes back to the historical features. Markovnikov didn't even know we had electrons. There's no concept of charge. He just notices where the hydrogen appears. Most of the time it goes to the least substituted position, but every so often it appears to show up in the most substituted. Okay? The most substituted substitution is against or an exception to my rule, so we'll call that anti-mean. That's all it is. Okay? If we follow the charges in the balance of those electrons, there is no exception. It's following the exact same rules that it followed in the Markov-Nikov additions. But you have to track the charges. You have to have some concept of positive and negative. Okay? Can we scaffold even higher up to the 5-membered or even 6-membered? Yes. Okay? The example being shown here is osmium tetroxide. Okay? What happens is our pi bond comes out and attacks. Okay? We have a pi bond to that oxygen, which means that oxygen needs a leaving group. That leaving group is pi bond, is those pi electrons. Are pi electrons particularly stable? How many times have you just looked out and said, oh, there's a pi electron just chilling out there? No, doesn't happen. That's because they're insanely unstable. So as it shifts out, it shifts through the rest of the molecule and forces more electrons to come out. The result is that we end up with 2 new sigma bonds for our addition, and we've kind of disrupted the rest of that structure. Because those pi electrons were not stable, they immediately interact back with the alkene, and we lock into that ring structure. That immediate part is important, because if we look at those 2 new sigma bonds, because they formed simultaneously, those 2 new sigma bonds are on the same side of the pi bond, and we get, again, the syn addition. So anytime I see the osmium tetroxide, I know that when it adds on the same side. That, again, gives me that stereochemical aspect that I need to know. I either memorize what it does, or I have some vague understanding of the background behind it. Okay? What I'm trying to show you is that vague understanding. You can memorize all you want. Kind of make sense? Okay. So let's take a little bit closer at the tetra intermediate, just because it shows up. Our Lewis structure for BH3. Okay. sp2, it has that empty p orbital. That empty p orbital is what can accept the electrons from our pi system. Okay. So if I went through and looked at a 2Z butene, okay, so we've got the 2Z butene shown. Z, because our large groups are, yeah, you suck. Everybody laughs at me when I do it. On the same side, trying to at least get you to do it. Okay? They're on the same side. What happens when we add the borane reagent? Okay? Well, we form the bond with the boron there. We form the bond with the hydrogen over here, and we lose that one in between. The result, there's our BH2. There's our hydrogen. Just our rough skeleton structure. Do we have any stereocenters? Do we have any stereocenters? Yes. Okay. Are we concerned about those stereocenters in this structure? And this is where Wyatt might be jumping in. Not particularly, okay? Because the mirror image of that can also form. How can the mirror image of that also form?
Rotate it.
I can't rotate a pi bond. I don't accept that.
BH attaches to the other side.
The BH attaches to what other side? Other side of what?
The pi bond.
The pi bond, because the pi bond is made up of,
Electrons.
where are those electrons located?
A little.
In p orbitals, and the p orbitals are both above and below. So we end up with 2 products coming out of that because of the nature of the pi bond. Okay? And where Wyatt, I think, was probably alluding to is that the other carbon here is not a stereocenter. So I'm not as concerned about that. But what if I locked in a ring? Okay. Now what happens? Is that other position a stereocenter? Yes. That is now a stereocenter, which means I have to specify wedges and dashes. We could go, well, it's just an enantiomer, so don't worry about it. No. This comes to how the boron and the hydrogen were added. They were added in a Syn addition, which means if I make, let's erase that hydrogen over here now. If I said that this methyl was wedged, what is the other methyl must be? It must also be wedged, because the boron and the hydrogen were added to the same side. Those would have to be dashed. Kind of make sense? Anybody want to freak out a little bit just with how I poorly drew that structure? No? Okay, thank you. Come on, really? The dashes are going up? No one want to look at that and be like, that's an awful way to draw that? Yes, it's an awful way to draw that. Okay, that would not get credit in smart work. Okay, on an exam, that's fine. But that's not going to get credit in smart work because we can't physically do that. Okay, there's no way you could orient the molecule to make that drawing valid. Okay, that's why it's bad. Okay, so if we were to clean that up to make it valid, we could make these wedged because that makes sense with them going up. And then we could make these dashed. Okay, even that gets a little bit wonky. Okay, we could switch it to the Haworth projection, in which case I can just show solid lines because in the Haworth I'm assuming up-down with that drawing. Right? We good? Particularly around rings, it's a super common ACS question with the borane. Okay. So, do we need a second reaction? If we looked at the product of that, we had boron attached to it, right? To the carbon. If we go, oh wow, there's a lot of steps. If we go all the way back to this one, remember the product of that lower left-hand corner? We had mercury attached to it. When we think about organic molecules, do we think about mercury?
No.
When we think about organic molecules, do we think about boron?
No.
No. Guess what has to happen? Almost. I would argue we actually don't have to think about it. We have to get rid of it. I don't want it attached to the structure. Okay? Which means I have to add a second step. Okay? And that's what this is saying. Do we need a second reaction? This is not a mechanistic thing. This is an actual second reaction. Okay? New reagents. I can't run the borane reaction, the addition of hydrogen and boron across the structure, like this. If I get rid of those steps. That is now invalid. That does not add hydrogen and oxygen. Okay? That does nothing. Okay? If I want it to do something, I have to show it as the individual steps. Okay? Which means we're adding a new reagent, which means we're potentially adding a new mechanism. Do you want to learn a new mechanism? No. Good answer. I would agree with you. We don't need to worry about it. Okay? So if you see odd elements attached to your structure, so carbon, hydrogen, nitrogen, oxygen, halogens, all of those are fair game. Okay? If we see boron, mercury, osmium, manganese, okay, iron, if we see any of those other reagents, those things need to somehow get cleaved from the structure. That's going to require a second step. Okay? Sometimes it's a really difficult one, sometimes it's not. Okay? What is that reagent? Well, if you don't know the mechanism, guess what you have? You just need to know the reagent. You have to have it memorized. Okay? And that's really all I can do for you. When it comes to the borane one, our BH3, come on, pen. Our intermediate, our reaction intermediate, not our mechanistic intermediate, was that we had hydrogen and our borane attached, our boron. What am I trying to get rid of? The boron. This reagent is known for adding hydrogen and OH. What have I added already? Hydrogen. Guess what the next step needs to do? Add the OH. Okay. And the mercury reagent. What have I added? The OH, so what do I need to add?
Much.
H. Okay. The H, I would argue, becomes a tricky one because H can be added in a couple different ways, either as positive or as negative. Typically, we see it as positive. We're trying to get the mercury to leave, which means mercury takes those electrons with it, which means the species we have to add in has to be negative. That means I need a negative hydrogen. Is that easy? No, there's really only two sources. Sodium borohydride or lithium aluminum hydride. Those are really your only two choices. Okay, when it comes to the mercury one, we'll typically only see sodium borohydride, NaBH4. Okay, so you just kind of have to know those extra steps. Make sense? Okay. The workup on the mercury. Okay. So when we go through and do these, yeah, I'll just draw the starting. What we started with, whoops, was this guy. When the mercury reacts, HgOAc2, mercury had a great leaving group, which means it doesn't fit in the tetra intermediate, it's a tri-intermediate, which means I get mercury attached. Right? Mercury is now a great phenomenal leaving group. What do I need? A nucleophile. What is that nucleophile? What is the characteristic of that nucleophile? Electron pairs. Okay? Typically when we're looking at it, we're looking at adding an oxygen. Oxygen has 2 electron pairs. Cool. Typically when we look at it, we see it with hydrogen. So that I end up with an OH, right? What did that now red hydrogen do in the course of this reaction? Rhymes with something. Nothing. So what could that hydrogen be? Well, it could be a hydrogen. It could also be a CH3. Okay. So when we're looking at our reagents, what we need to focus on is what's the important chemistry. The rest of those pieces, I don't really care. It didn't do anything. Don't worry about it. Leave it attached. Okay. Could I have shown this instead of, actually even before we do that, what compound is that? What functional group?
Alcohol.
It's an alcohol. I can react the mercury with an alcohol or water. Both are valid. That was not the button I meant to push. Could I have reacted it with does it have lone pairs? Yes. So couldn't those theoretically share with it? Causing this to open? What would the result look like? Everybody agree? What is the problem with that structure? Positive charge on the oxygen. If I had done it with an alcohol, what do? The oxygen steals the electrons from the hydrogen, and we have hydrogen drift off. Can I do that? Hey, that was cool. Can I do that now? No. I can't have that methyl group leave. So where does the oxygen get the electrons from?
The bond it just formed.
The bond it just formed, which then means I'd have a positive charge, which needs to be stabilized. What happens?
Go back to square one.
It goes back to square one. So when we're looking at our reagents, we need a nucleophile. We have electrons. But we have to think about the next step. Does the next step lead to something more stable? Okay? And in both cases, if it was an alcohol or ether, the answer is no. But what does the ether have? Another step that allows me to become more stable. Okay? So it's always about looking at probably 2 or 3 steps down the road. Okay? Anybody good at chess? If you were good at chess, you'd be great at OChem. I suck at chess too. Okay? We have to be able to look down that path. If you can't see that in your head, what do you need to do? Write it out. Okay? Draw out each of those steps. Look at the result and be like, this sucks. Oh, but I can make it better. Oh, I still can't make it better. Then you screwed up. Go backwards. Okay? So when we look at our mercury reagent, we're trying to get rid of that mercury. Okay? It needs to take those electrons away. That's where we're supplying H minus. H minus is not a stable reagent. We need something to temporarily stabilize that. That's where the boron comes in. Okay? The boron can coordinate with the mercury. The hydride can coordinate with the carbon. And we end up with our final result. The hydrogen's attached, and we completely ignore it because it's hydrogen, and we imply hydrogens. Okay? Kinda, sorta. Or no. Lots of processes we're moving through. Again, what I'm trying to get out of this section, this is ultimately, I think, chapter 10, 12. It's chapter 12. Okay? Is that I want you to look for larger patterns, not so much the reagents. Okay? Yes, you're tested on the reagents. That's going to require strict memorization. That's practice. Okay? If we can get at the patterns, that can help with that memorization. Make sense? Okay. Our tetra intermediate, how do we remove the boron? Okay, this is where we bring in our peroxide and hydroxide and it ends up exchanging it out. Okay. I kind of cheat on this with my own little hand wavy mechanism that is way wrong for the record. Boron has that empty p orbital. What can I put in that empty p orbital? Electrons. But now boron has too many electrons. What does it do?
Cleaves off the carbon.
Cleaves off the carbon, but now that oxygen has too many electrons. The result is, where did the OH go? What does it look like? Where did it go? Where the boron was. Can you get more specific on that? The exact position. Like, well, yeah, I see, it's at the same carbon. No, no, no. The exact position in space. Notice where the OH is. Notice what happened to the wedges. They stayed wedges. We get a maintenance, if you will, of stereochemistry from the initial addition of the hydrogen and the boron. That is a nifty little reaction. If we think back to all our other ones, as soon as we do a second step and we do a substitution like we're doing here, what happens? We typically see an inversion or an additional product because it's a formation of a carbocation. Because boron is unstable, or not necessarily unstable, but has that empty p orbital, it has access to this kind of neat chemistry where it can do a complete one-for-one swap out in the exact same physical location and space that we couldn't get in any other reaction. Boron's kind of neat for that. Okay? So, I'll give you a couple minutes. Okay, so now that we got them all up, assuming I didn't make any last-minute mistakes there, okay, Wyatt had asked a question at the very beginning of this. He said, well, why would we choose boron or mercury? And he'd actually followed that up with saying, well, the boron is going to place the OH at the other position. Remember, our OH does, or our boron reagent does the anti-Markovnikov, does the opposite of what we would expect typically for hydrogen and OH additions. It's because the hydrogen is getting added as a negative. Right? So if we go through and start with the first one, we get two products, right? One for the boron, one for the mercury. What is the difference between those products? Nothing. Why? There's no way to distinguish them. There's no stereochemistry. There's no extra wedges or dashes or anything like that that we have to worry about showing or implying. And then if we compare those products, there's nothing to compare the difference between. So why would I choose one reagent over the other? Which one do I happen to have on the shelf? That's how that decision gets made. For the next set, moving down on the left. Okay. What do we notice as differences between those products? More substitution makes me nervous because it's not a substitution reaction. There's an extra methyl. There's a methyl in comparison to the previous one.
Yeah,
Yes,
yeah, that's
I'm with you. Okay. We have an extra methyl group on it, so that now changes the dynamics of that alkene. Does that dynamic change affect the products that we see? Well, yes. Now I can tell a difference between them. What are those differences? I now have a stereocenter in the case of the boron. I don't end up with one in the case of the mercury. Okay, so the mercury, I don't have to worry about wedges and dashes. I do have to worry about it in the case of the boron. And that might actually be an enantiomer. I may have done that too fast. I'll just draw the other product. Yeah, I think it's an enantiomer. Why do I get those two products in the case of the boron? So what's the number one difference we see? We have stereochemistry. How many of you are like stereochemistry? I totally own that. Okay, so let's skip the stereochemistry and look at location. I know my arm belongs on the side of my body up towards the top where the shoulders are. It doesn't belong out of my knee. Okay? Yeah. So what's the difference between the products, red and purple? The OH is in a different location. Why? The boron reagent does the opposite of what we would typically expect. Mercury follows what we typically expect. So one answer is, I know boron does the opposite of what I want, so I'm going to do what I want, and boron does whatever the opposite of that is. Okay? So you are saying that my answer is going to be wrong, so I'm going to guess the opposite of my answer. Fair enough. That works. Okay? If we go back to the mechanism, boron gets added as the positive. The positive goes to the most negative carbon. If we look at resonance, the most negative carbon of our pi bond is that one, the most positive being the other position. BH3 adds the negative hydrogen to the positive spot. That's why we get the OH appearing in the other location. Okay? Back to the stereochemistry. What's going on with that stereochemistry? What are we adding when we add the boron reagent? There's two things. Good guess. Hydrogen and OH. Those are the two pieces we're adding. That's what's changed as we moved across. With the boron reagent, the hydrogen and the OH, because it's kicking out hydride in that initial addition, that's a very small group. So the hydride and the boron add on the same side of the pi bond. So when I go to draw my product, the OH has to be on the same side as where the hydrogen would be located. Why was the hydrogen not shown? Because we can imply hydrogens. By showing it, I now know that if that hydrogen was wedged, the methyl group that was at that position must be dashed. Why do I need the second product? Boron could have attacked the pi bond from the top or the bottom. That changes that stereochemical arrangement. I have to show both. Make sense? Upper right corner. I add the BH3. I end up with my product. Notice no stereochemistry. Okay? Because the OH is coming in at a position opposite of what I would expect based off the charges on these. Okay? In the case of the mercury reagent, it comes in exactly where I would expect it to be with the charges. Make sense? In the case of the mercury now, I have a stereocenter. I have to specify it. I have to say I've got enantiomers. Okay? The only reason that's showing up where I'm really keying in on that is if we go back to the previous one we looked at, we could say, oh, well, mercury reagents, we don't worry about stereocenters, and boron reagents, we do. Is that true? No. It's always going to depend on the new situation you're in. You can't make a blanket statement like that. Okay? So you all good with the rest of all those? Okay? So with that, Let's go ahead and look at the last one. So I'm going to guess more than Amber just had a question on that. Both of these reagents should add what? H and OH. Two nonpolar pi bonds. Is the alkyne a nonpolar pi bond? What are the atoms of the alkyne? Carbon and carbon. Is that by definition nonpolar? Yes. Same electronegativities. So it is definitely nonpolar. Do I have a pi bond between them? Yes. Guess what the alkyne does? It is a nonpolar pi bond. It follows the exact same rules that our alkene does. Okay? So why on earth then do I not get the addition of hydrogen and OH? I do. I do get an addition of H and OH. Sure as hell doesn't look like it. What the heck happened? So let's look at the boron reagent, because that's what our slide is. Okay. We would expect the OH to go to the end. So there's my OH. There's my H, right? We added that. Everybody happy with that? Okay. My students don't have an out from first semester. What functional group is that? That is an alkene and an alcohol at the same spot. It's an enol. Enols are inherently unstable and will go through what is known as a tautomerization. Tautomerization. Okay. The oxygen can steal electrons from the hydrogen, which then puts negative charge on that carbon. Come on. How can I stabilize that negative charge?
Add a hydrogen to it.
I have added H and OH. It just so happens that that reagent or that intermediate structure rearranges itself to form the carbonyl. If we had two nonpolar pi bonds with our alkyne, wouldn't we expect two additions of H and OH? Well, yeah, that makes sense. That's what the nonpolar pi bond does. But as soon as I form the enol, it changes to the aldehyde. Do I have a nonpolar pi bond anymore? Nope. It won't continue the reaction. It stalls there. Okay? For those of you going, wow, that's kind of crazy. I wish I'd learned that. You did, theoretically, in first semester. It was one of the reagents that was showing up. It's one of those kind of curveball reagents that usually gets thrown at the end, just says, hey, this is what it does. And you just have to memorize it. It's doing the exact same chemistry. You're adding H and OH, period. Okay? You're adding it in the exact same locations that you would according to those reagents. The issue is the product shown then rearranges itself to get you a carbonyl. Those who are going, well, at least we don't have to worry about that functional ever again. 90% of second semester OChem is centered on the enol. 90% is a bit excessive. It's probably like 60, 70% is based on the enol functional group. Anybody moving into pre-health kind of professions? Is that where you're trying to go, right? Almost everybody. So like biochemistry might be on your plan, take a biochemistry class. Roughly 90%, and this one's not a lie, 90% of biochemical pathways move through an enol. Okay? It is incredibly important as an intermediate. You need to remember it. You need to recognize that as soon as you form an enol, that's going to rearrange to the carbonyl. As soon as you see a carbonyl, you need to think that could become an enol. When and why it does that, that's what we'll talk about later in the semester. Okay? So what happens with the mercury reagent? Well, the mercury reagent still adds H and OH, but it's adding the OH to the interior. It's still going to form an enol. It's just going to now form the carbonyl at that other location. Kind of, sort of? Okay. That's all you get. Almost. Okay. Did you want the boron reagent mechanism? Probably not. If you do, go to the slides, look at it. This came from one of your textbooks. The biggest thing to get out of the mechanism on getting rid of the borane is your stereochemistry is retained or maintained. Okay? You don't do an inversion of stereochemistry. Your boron and your OH come in at the exact same location, exact same position. Everything is maintained. That is your official mechanism. I know instructors at ASU, for those of you that have had ASU, go through the details of that. I don't think it's worth my time. Or for that matter, yours. Okay. So our alkene addition summary. We have pretty much covered a large portion of this. These sections here were our chapter 11 in our textbook. We just did boron, mercury, boron, doop. That was chapter 12. Okay. We've got 2 reagents really left on this chart to worry about. This guy, which is our radical. That's chapter 25. If you have questions, you can ask them after class, but that's about as far as we're going into that one. And then this last one, I wish I could tell you which chapter it was, but it is a chapter that is somewhere between 7 and 26. Honestly, I don't remember where it's showing up. Okay, but it's in one of those. Okay, maybe I've got it on the next slide. So take a step back. Let's zero in on that reaction. Gen Chem. Yay, Gen Chem. What kind of reaction happened there? It's a reduction. Okay? So, well, I don't even recognize how that could be reduction. Okay? My first semester students, again, I've shown you that slide. You better know. For everybody else, you might be looking at it and say, well, I have to do oxidation states and all that nonsense. Yes, theoretically we could. Okay? If we go through and look at redox, as we remembered from Gen Chem, redox, okay, we have gain of electrons. Seriously? Gain electrons R corresponds to grr. Totally done. I just want to see if you guys are paying attention. Loss of electrons, oxidation is Leo. Okay, or you might have remembered oil rig. Okay? If we go through and look at our organic chemical reaction, can we tell about the transfer of electrons? And we look at it and go, oh, that is totally this. What species was oxidized? What species was reduced? That becomes a lot more challenging to deal with. So we don't want to use those same rules. Even though those same rules are still valid, they're just harder to interpret. Oh, there you go, chapter 19. See, I was right. It's between 7 and 26. So our organic chemistry tweak. Reduction is an increase in hydrogen bonds, okay, or a decrease in oxygen bonds. Oxidation is then going to be the flip of that. Increase in oxygen bonds or a decrease in hydrogen. So if we take a look at our reaction here, where's the chemistry occurring? Where the pi bonds are. So we're looking at these carbons. Okay. What happened to those carbons in the process of becoming the product? Well, we draw on all our bonds. What happened to those carbons? They gained hydrogen. So those carbons were by definition reduced. We would reference that reaction as a reduction reaction, not redox anymore. Even though oxidation happened, we only refer to it as a reduction because I only care about the organic molecule. I don't care about anything else. What happened to the organic compound? The organic compound was reduced. That's a reduction. Right? So we'll start with classifications between reduction reagents and oxidation reagents based off of this. Okay? Does it have to be oxygen? No. Okay? And really, I need to go back and edit this slide, and someday I will do that. I would argue that a better way to look at this, instead of oxygens, is a decrease in, and this is why I haven't done it, electronegative atoms. okay, in both cases. Okay. A decrease in the more electronegative atom bonds is a reduction. An increase in the more electronegative atom bonds is oxidation. If we go through and apply that back to this, okay, yes, we could use hydrogens, but now I'm saying you can't use hydrogens. I want to look at the more electronegative atom. Let's take a look at that lower right-hand carbon. Okay, let's call it carbon purple. Yes, it increased the number of hydrogen bonds, but I said we can't look at hydrogen. What's the more electronegative atom? In particular, since this is a reduction, I know it's a decrease in the more electronegative atom. What more electronegative atom did I get rid of? Carbon, so I don't have a carbon anymore? Ah, see, there's the issue. Yes, it means I decreased the bonds to a more electronegative atom. Is carbon more electronegative than carbon?
Nitrogen, yes.
Than carbon? It's where the chemistry is occurring. The chemistry is happening to that carbon. So yes, I've lost a bond to a carbon, but that's not more electronegative. It is more electronegative in our definition. What is the hybridization of the carbon that I lost a bond to?
SB2.
sp2. What is the hybridization of the carbon that it is still bonded to in the product?
SB3.
sp3. Which is more electronegative, an sp2 atom or an sp3?
SB2.
An sp2. There's my loss in electronegativity. Okay? I lost a bond to a more electronegative carbon. Okay? It was more electronegative because of the hybridization. Hybridization still plays a role all the way through. Okay? So you can run into weird gray area ones that are looking at electronegative atoms. Okay? Sometimes they hit hybridization. You can usually sneak by looking at our hydrogens. Kind of make sense? Questions? Far away. Done. Oxidation states. Okay? If you want to determine oxidation states, by all means, talk to me after class. It is not worth spending any more time than saying that is a rule. You could use it to determine them. Take a hot second or two. Label the 6 reactions as reduction, oxidation, or neither. We could have neither as a valid answer. Do you have any questions about those assignments? Again, my first semester students have already seen it, so I'm a little bit less concerned about you guys. Everybody else, what do you guys think? You're like, I challenge that. I don't understand how you got that answer.
How come neither?
How come neither for which one? Oh, there's only one. Never mind. Sorry. How come neither for this one? Right, this is where it can be tough. So we want to identify where our chemistry happened. Our chemistry happened at this carbon. So I don't care about anything out here, anything out here, anything out here, or anything out there. I only want concerned about what happened to that carbon. So on the reactant side, what happened? Well, I lost a more electronegative. Chi is our symbol for a more electronegative. We lost a bond to the chlorine, which was more electronegative than the carbon. Look at the product, what happened? What's that? We gained a more electronegative. So loss of an electronegative element would mean reduction, right? But I gained an electronegative element, which means oxidation, which means they cancel each other out, and I'm left with neither.
So hydrogen doesn't matter.
Did hydrogen change at the carbon? No. Okay. Yes, there's a hydrogen attached to that oxygen out there. But if I went through and said this then, did the hydrogen change? No. The chemistry still only happened at that carbon. That's why we keep the focus on that carbon and that carbon alone. It's actually one of the reasons why that question was picked. Okay? So it's not looking at the overall structure on all the pieces that came in, but what happened physically at the position where the chemistry is occurring. Make sense? So the rest of those good? Okay. We will talk about the reagents that do all of those by the end of the semester. Okay. At this stage, all we're really concerned about is our alkenes, our nonpolar pi bonds. Most of those aren't that. Okay. So our alkene oxidations, if we go through and apply that rule to all of these, we're starting with our alkene in the dead center, and we're going out to varying extents, any other direction. We're gaining more electronegative atoms in all those cases. Okay? We're adding oxygen, so it's an oxidation reaction. Okay? You're responsible, again, for knowing all of those reagents. We've already actually talked about one of these. We've got OSO4 up there. Remember I showed that? That was this guy. I had the oxygen, double bond, osmium. And I said the pi bond came out attacked, where the oxygens were now added on the same side of the pi bond. But I don't like osmium, so what do? I get rid of it with a second step. That second step cleaves the osmium, leaves the oxygens behind, and I'm now left with my diol. Okay? Diol, di meaning two, all for alcohol. Okay? Notice what's particularly interesting about that addition. Number one, their stereochemistry. Number two, where did those alcohols go? Same side. It's a syn addition. So by knowing something about how the reagent classifies, I can start to predict that stereochemical arrangement. Okay? That's the point of those previous slides. Trying to classify these reagents into those buckets. Okay? They aren't perfect buckets. They've got a lot of holes, like my analogies. Okay? So our penta intermediate, we've got our metal in the center of oxygen, okay? And then ozone. When we're looking at coordinating those with a pi bond, in fact, I think I have, yep. With our pi bond, we're doing the same kind of thing. The pi bond comes out, shuttles electrons. We have 1, 2, 3, 4, 5 atoms in a ring. There's a cyclopenta. Okay? 1, 2, 3, 4, 5 cyclopenta. We're looking at that kind of penta intermediate in all of these reactions. Okay? That works for the osmium. It works for the ozone. When we look at O3, that's the arrow to the left. And if we go straight down, we're looking at KMNO4, where the metal is now manganese, not osmium. Same basic pattern behind how it fits and how it reacts. Okay? We've also seen this with the Diels-Alder, okay, in chapter 24. Okay? Because the lab has officially covered it, I will be opening access to that video. Hopefully at some point today. You should go through and review the answers to the Diels-Alder reaction. Okay? We'll talk about that next Monday. Make sure you've got at least a baseline on your Diels-Alder reaction and you can get some kind of feeling for what's going on with that, for those of you that aren't in the lab. Same idea is happening with our osmium. Same kind of connections between those. Okay? In our Syn mechanism, pi bond comes out, reacts with the oxygen, shuttles around, and we end up with that goofy looking intermediate. Notice they're highlighting the fact that it has an enantiomer. Why does it have an enantiomer? Why the stereochemistry important? What can go on the bottom?
The osmium.
The osmium, because it's reacting with the pi bond, which is made up of p orbitals both above and below. Okay on that now? Good. Okay. And this is, I think I actually copied this off of their slides, and they're like, this is the mechanism for this. Notice where are our mechanistic steps? Right there. The following step has how many mechanistic arrows? Mechanistic arrows. Mechanistic arrows would be the curved arrows. How many curved arrows do you see? None. So we're saying, here's the mechanism for it, but I'm not going to show it to you. Okay? You can thank us later. You don't want to worry about that mechanism. You aren't concerned. Okay? If you see OSO4, you're going to the syn addition, the cis diol. Okay? For those that hadn't heard, cis is an adjective, syn is an adverb. Syn is describing the action of adding, cis is describing the location on the object. Okay? Hence the two terms. So if we were to predict the product for the following reaction, what would our product look like? That's a lie. Don't answer that, because the answer's already up there. Okay, so are we okay with that? Okay. Just pretend I didn't say that. Okay. Permanganate is kind of a new one now, because we haven't shown that anywhere, KMnO4. Okay? It is the same process as the osmium tetroxide. Okay? If we draw out the permanganate, we have the Mn, we have our oxygens, we can react, shuttles around, shuttles out. So we're getting the same system, which means we're adding the permanganate as a syn addition. I now have manganese attached to the structure. I don't want manganese attached. Where's the weird thing with the permanganate? If I don't want a manganese attached, what do I have to do? I had to do a second reaction. What's the second reaction? It's all together. This reagent runs as one step. We can put it all in at once and it does it all together, and it drops us out at the Syn diol. There's some really big conditionals that come out of this. Typically when we think about our reactions, we just add the reagent. Notice we're not just adding a reagent here. We're also adding hydroxide, and we're also specifying a temperature. We're calling this cold, which will become super, super important a little bit later down. Okay, which might even be the next slide. But notice the bold thing saying assume. You see KMnO4, cold, cis diol. Okay? Same basic understanding as the osmium tetroxide. Okay? Why accent that? Don't worry about the mechanism. What if we tried to predict the product for this guy? What would happen? Okay, we're going to have to show the arrow, reaction arrow going backwards. Okay, and you should already be panicking a little bit, because what do you see?
Alkyne.
An alkyne. We know the alkyne does some weird stuff. Okay, so let's go through and evaluate. 1, 2. Our rings. I'm just going to draw circles. Okay, we would do our cis diol, right? What functional group is that? It's an enol. What ends up happening? It tautomerizes. What is that? An enol. You can mechanistically draw it all out. It does work. What you will end up finding, whoops, is you will end at this for an answer. Okay. You'll move to the diketone. Okay. You're still forming that enol. That's going to immediately start sending you towards the carbonyl. You got to watch out for that. Because you have that other alcohol there, the chemistry will associate and it flips on top of itself effectively, and you get the diketone. Just kind of a weird one. Just thought I'd throw it in there because it looked kind of interesting.
What would keep it from adding 4 OH groups?
And this kind of goes back to the balance between the enol and the carbonyl. Once we have a carbonyl, do we have a nonpolar pi bond anymore?
No.
No, which means permanganate can't add.
Okay.
Okay. Remember that statement that I just said. We don't add the 4 alcohols in like 3 weeks. And you can be like, but you said, and yes, you can do that then. Right now, 2 carbonyls. Okay. The next big one that comes out of this chapter is oxidative cleavage. Well, we've already talked about oxidative, right? We added oxygen. Okay, so if I start with a nonpolar pi bond and I add oxygen, well, that's by definition an oxidation. Okay? What if I do oxidative cleavage? What am I going to have to do?
You add 2 oxygens. Or you break them.
I'm going to break the bond, but I had to break a bond anyway to put the oxygen on. The bonds that made up the connection between those 2 carbons, if I'm going to say cleavage, it's gone. Completely separated at that position, replace those bonds with oxygen. Oxidative and cleavage. Okay? So if we take a look at the alkene example that they're showing up top, Okay? We take our pi bond, we say, okay, I want to oxidize, so I'm going to put on some oxygens. So there's one, there's the other, okay? But I need to cleave both bonds. Okay, so I can bring in my, butcher knife, right? Butcher knife, little circle, or a dinosaur head. Chop, gone. I need to replace those two bonds with oxygen. I've already replaced one with oxygen. How do I replace the second? Well, I make it a pi bond. I now have two bonds to an oxygen. The example that I gave first semester was that if you ever suspect you're doing oxidative cleavage, we can worry about mechanism if you want, okay? That's a lie, actually. We're not going to worry about mechanism. Is just stretch the crap out of that pi bond. Don't change anything about the arrangement of those pieces, but stretch it out. Since you got a pencil, erase it, draw an oxygen, Guess what? Done. You've now done oxidative cleavage on an alkene. What happens when we move to an alkyne? That's a little bit trickier. When we're at the alkyne, I have 3 bonds to replace, and I would argue that they kind of goofed on their demonstration here. That means when I go through to make the product, how many bonds to oxygen do I need on my carbons? 3. How many bonds to oxygen do I have shown? Only 2. Where's that third bond? Not shown. We'd end up with carboxylic acids when we oxidatively cleave those. Okay? Some of that depends on the extent of our oxidation. Okay? The reagents to remember for this, the big one is permanganate, KMnO4. The other big one is ozone, O3. Your textbook also mentions that you could do in a 2-step reaction OSO4 followed by periodate. I'm not going to talk about the periodate. That matches the patterns that we've seen everywhere else, right? Except instead of it being a metal, we have iodine in the middle. But periodate acts pretty much the same way that permanganate would do in the oxidative cleavage situation. Okay? So let's push through and take a look at our permanganate. One of the big things that comes out of this is that we change the reaction. If I take a look at my alkene, I'm adding permanganate. Well, that would suggest that I would end up with the diol as my product, right? Diol. What else would I add to that? Yes, wedges and dashes, because it is a syn addition, Mike. Because it's pi bonds, and they're adding on the same size because that Cyclo penta intermediate, right? Okay. But to get the syn addition, what were the conditions of that reaction? Dilute and cold. I don't know about you, but I don't think dilute is spelled C-O-N-C, and I don't think cold is spelled 50 degrees Celsius. Okay. So there's some modifications going on here. Okay. We still end up with our cyclic intermediate. That's still how it functions. Okay. That would still go through, whoops, it jumps all the way to the full cleavage. That's what that reagent does. So why? How did it do that? That seems really bizarre for it to just chop it open all of a sudden. Okay. That comes back to looking at the strength of the oxidizing agent. Permanganate is a really strong oxidizer. Okay. So if we go back and take a look at our functionalities between here, we want to see what could potentially happen with our new functional group. If we're in water or a hydroxide environment, there's a nucleophile. Okay. Well, is there an electrophile present in that solution? I say, well, I don't know, what's an electrophile? What charge does an electrophile have? Positive. I don't see any positive charges in there. So no, I don't think there's an electrophile. Well, we have a kind of interesting sidebar coming here. What is our new functional group being shown here? It's not a ketone, we're getting at the right idea. Carbonyl, officially an aldehyde. Okay. We haven't talked about the reactivity of those yet. Okay, but let's think about it. What is the reactivity of a carbonyl? Should it match the reactivity of an alkene? Why not? It has a pi bond.
It's not, it's polar.
It's polar. The oxygen is more electronegative than carbon, which means what is that oxygen doing to the electrons in that high energy pi bond? It's pulling them towards it, meaning I get a resonance structure that looks an awful lot like an electrophile. Yes, we have the potential for an electrophilic atom. Okay? The functional group that we're looking at, or the transition, we will talk about again later in the semester. We're starting with our carbonyl. If I have that react with a nucleophile, particularly an oxygen nucleophile, an alcohol in particular, I can form what is known as a hemiacetal. If I have that react with another equivalent of alcohol, I can form an acetal. And this kind of goes back to your question about, don't I get 4 alcohols attached? With that carbonyl, I have an electrophile. With oxygen, I could have that oxygen attack, and I would get 2 oxygens bonded to it, okay? Like the hemiacetal or the acetal. Those structures are inherently unstable and favor the carbonyl stability. But if I'm in an environment of high heat, I now have access to all of those reactions. So what ends up happening is the alcohol or the hydroxide or water can attack the carbonyl, forming an interesting structure. What is special about that structure? Can we name that functional group? That one right there. What is that functional group? Right, should we try it this way? What is this functional group? An alcohol. How many alcohols are there in that red box? 2. How do I name 2 alcohols? Diol. What's our functional group? It's a diol. Okay. Technically, I think it's a vicinal diol because they're attached on the same carbon. It's vicinal or geminal. I don't remember which one. Have we seen diols show up before, particularly with respect to our metal oxide reagents? Yeah. Okay. What can happen is the permanganate can coordinate to those alcohols. Now what can it go through and do? It can go through and do the exact same oxidation reaction that it did in the previous cases. The result being is that I go all the way down to the carboxylic acid. Crazy. Okay. And all we had to do that is, instead of being cold and dilute, be concentrated and hot. And all of a sudden that scaffolds all the way out. Kind of, sort of? Okay. With that, we've got some practice here. This one should look really familiar because we just did it. So what's our quick and easy, dirty way to do this? Stretch the double bond. Draw the rest of the structure out. Right? Erase the middle. Put in oxygens. Okay? That's our step 1, our oxidative cleavage. Permanganate, really strong oxidizer, which means if it can oxidize, it will. To oxidize, what has to happen? This goes back to the definitions that we started our redox section with. Increase bonds to oxygen and decrease bonds to hydrogen. Where's the chemistry occurring in this reaction? Which carbon? The carbons of our pi bond, right? Okay, so I did my oxidative cleavage there. I'm in a strong oxidizing environment. So if I can oxidize, what should I do? Oxidize. So I will look at those reactive carbons and say, can I do more oxidation? Do you see any hydrogens there? There are implied hydrogens. Do I have hydrogens I could get rid of? Yes. Could I replace those hydrogens with oxygens? Yes. The result of your permanganate reaction is those become the diacid. Right? Notice we have a step 2. Why a step 2? We're adding HCl to form what functional group? Carboxylic acid. We're in a basic enough environment as the reaction runs that we need to add an acid to fully protonate. Okay? That's why that step 2 is there. Okay? I know we are officially done, and I promise we're almost out of here. If you got to leave, feel free to go so or do so. Right? There's our other one. We'll run the same logic. Erase, oxygen, oxygen. Because this is permanganate, stupidly strong oxidizer. If I can oxidize, I will. Is there a hydrogen connected to my purple carbon? No. So can I oxidize? No. Is there a hydrogen connected to my blue carbon?
Yes.
There's an implied hydrogen there, which means strong oxidizing agent. That needs to become OH. And I've got it done. Okay? Where we will pick up on Monday is not with this slide, or not exactly with this slide, but with these structures. Right? Slightly more advanced. They are in the slides if you wanted to go ahead and do it, but they're buried underneath these images. So you'd have to click on those and delete them, or you can just draw them right now.